I am Elena Vigna. I am full professor in applied mathematics at the ESOMAS department, and in this short video clip, I will share with you part of my research. I am a mathematician, and therefore I use tools from mathematics to solve problems that arise in economics, in finance, and in insurance. One of the main areas in which I do my research is pension. As you probably know, every pension provision system is made by three different pillars: the state pension, the pension from the pension funds, and then individual saving. I focus on my research on pension funds. There are two different types of pension funds: defined benefit and defined contribution, and my research is on defined contribution pension funds. When you do research in defined contribution pension funds, you can do research either in the accumulation phase, which is the period between joining the scheme and retirement, or in the decumulation phase, which is the period between retirement and death. I've done my research in both periods, both in the accumulation phase and in the decumulation phase, but here I show you something about the accumulation phase, which is the period between joining the scheme and retirement. Here is a list of possible problems which you can solve in the accumulation phase of a DC pension scheme. F of n is a quantity which you want to optimize, for instance, final wealth time n, or the replacement ratio time n. The replacement ratio is the ratio between pension and final salary. So, for instance, you want to maximize expected final wealth subject to a fixed variance of final wealth, or you want to maximize expected utility of final wealth, or you want to minimize the square of the difference between final wealth and the target, so you want to hit the target. And in all of these cases, your control variable is the investment strategy. So you can decide what is the investment strategy that maximize or minimize your criteria. That is, you want to find the optimal investment strategy to be adopted in the period between joining the scheme and retirement. As an example of my work, here is this paper, Mean Variance Dynamic Optimality for DC Pension Schemes. This is a joint work with Francesco Menoncini. So first, we define the financial market, and there are three different levels of complexity for the financial market. The first level is this one. You have S state variables, which describe the uncertainty, basically, that can affect the financial market. Then there is one riskless asset with the riskless rate R, and then there are N risky assets. So you want to find the optimal investment strategy, which is given by the vector WT, which reports the quantity that are invested in the risky asset. C is the contribution rate and X is the wealth. This is the equation that governs the stochastic differential equation that gives you the growth of the wealth over time. In a more specific case, you can have, for instance, two state variables, which are stochastic interest rate R and stochastic contribution rate. The contribution rate is typically stochastic because it is a percentage of the salary, and the salary is stochastic. And in this case, the wealth grows according to the stochastic differential equation number 4, where the control variable is WT, again, a vector that reports the quantity invested in the risky asset. In a still more specific case, you have the Black-Scholes financial market, which has a riskless asset with the riskless interest rate R constant, and the risky asset whose price follows a geometric Brownian motion. And the question number 5 gives you the wealth, the equation of the wealth, where WT is the investment strategy and is the amount invested in the risky asset, and C is the contribution rate. This is the financial market, and then the criterion. In this paper, we define the criterion was the mean variance. So you want to maximize expectation of final wealth minus alpha, the variance of final wealth. So basically, you want to maximize the expected final wealth, but you want to minimize the variance of final wealth. So this problem is the mean variance and is time inconsistent, in continuous time. And there are three different approaches to deal with a time inconsistent problem. One is pre-commitment, 2 is the dynamic optimality naive, and the third one is consistent planning. In this paper, we focus only on the first and the second approach, and we want to compare pre-commitment and dynamic optimality naive. And in all of this financial market, we find the optimal investment strategy in closed form, and then we do some simulation in the Black-Scholes financial market. These are the assumptions on the simulation. And we find some conclusion. As a theoretical result, we prove that on average, the wealth growth over time is exactly the same. Then, because of the simulation, we find that In the pre-commitment case, the standard deviation of final wealth is lower than in the naive case. So this is good for the pre-commitment. But in the worst scenarios, the pre-commitment wealth is definitely worse in the pre-commitment case than in the naive case. Regarding the strategy, on average, the pre-commitment strategy is less risky than the naive strategy, but over the scenarios, the pre-commitment strategy is more volatile than the naive strategy. These are some of the results. I hope that you enjoyed the talk, and I wish you a lovely day.